Okay folks, we are going to prove that the angle bisectors in a triangle are concurrent. Now, to be able to prove that, I've done a little construction here for us. Let me just discuss this with you in Sketchpad. I've drawn the angle bisector AD that bisects angle ABAC, and I've drew it in a thin red line, and then BH, or B, which one is it? BF. That is the angle bisector of angle ABC. I found the point where they intersect, and that's point P. So what the problem is now, we've got two angle bisectors. We've got the point where they intersect. We're happy with that. We now have to show that EC, which is an angle bisector, contains the point P. Okay, so in other words, that P also lies on EC, and with that we can argue that the three angle bisectors are concurrent. Now the theorem that we would so much love to use here is Ceva. Ceva says something about triangles. He says the following. Now follow the cursor on the screen. We want to show that FC or CF over FA multiplied by AE over EB multiplied by BD over DC is 1. Ceva said that if that is the case, then these Cevians, these lines here, the red lines, are concurrent. And obviously at this point they'll be concurrent at P. Now folks, Ceva works with ratios. And for us to be able to work with ratios, we need either triangles, because triangles that are similar have sides in proportion, or we need a triangle with parallel lines, because that creates proportions as well, or ratios as well, that we can use. So either way, we have to have either a parallel line, or we need similar and or congruent triangles. Once we've got these two in place, then we'll see that Ceva will most probably hold. Okay, so what I'm going to do is I'm going to suggest that we remember these two angles are equal, those two there are equal, these two bottom ones are equal as well. So if I use point C, and before I go there, let me just drag point Q over here. This is something that we saw on our previous lesson, that if we want a point to be equidistant from two sides, or two non-parallel lines, which is what these two sides are, okay, and we move it, that these distances QL and QM over there remain the same. You can watch them. I'll put them in purple. As I drag point Q along, the side lengths of those two distances to the sides remain equal. Now remember, the shortest distance from a point to a line is the line that runs perpendicular to it. Okay, so we can see that, and that's a property that every single angle bisector will have. I've used the 2 points where the point where these two angle bisectors are concurrent to draw the incircle. That is called the incenter of the triangle. And I want to show that that incenter also lies on the third angle bisector. So let us construct, let us choose point C maybe and go for AB, and let's construct a parallel line. Now I'm going to make that parallel line dashed, and I'm going to make it what? Thin. Not hairline, thin. Okay, so there we go. We just move these two out of the way so we have place to write. Okay, so I've created this line here, which is parallel to that side. Now, what does it mean to us? Well, it shows us that this angle here at A is equal to this one here. Alternate angles that are equal. It's also this angle at B is equal to this full angle here at C. Alternate angles that are equal. Okay, but now look at this. I still don't have a triangle here. that I can use to prove either congruency or similarity. So I'm going to tell the computer to select that line, I select that line, I select this point. I construct a parallel line there. Now that parallel line then intersects, not parallel, yeah, it's parallel to the Cevian AD, or the angle bisector AD. So if I now go and I construct the intersection of those two, this little angle here is equal to that single angle at A, alternate angles that are equal. I've also divided my diagram into, there's a triangle here, there's a triangle at the top, there's a triangle here and a triangle here at the bottom. I'm most probably going to use the one at the top, there, BDA, and D. Now let's just call this point, let's just call it point G for now. Okay, the computer called it point N, let's leave it as point N. Okay, so what we're going to do is we are going to prove that this is indeed the case. Okay folks, let us start with our proof. Remember what we did is we drew this side parallel to that one. Now I'm going to call this A1, A2, B1, B2 if we need, and we'll number the angles as we go along. What I also want to do is label the angles with X's and Y's so that we can easily identify them. So let me just get colors out of my bag and then we can go. Here we go. So if I say this is an X and that is an X and this is a small y and a small y, and C1 and 2 if we need will be Z and Z. Okay, so let's call this angle N1. N1 is equal to, so we constructed, NC was constructed parallel to AB. Okay, that was construction. And the reason for that is, we discussed, was because we're going to use Ceva, so we need some proportions out of this diagram. Okay, with that construction then done, immediately what can I fill in? That's 2x. So this angle here will be 2x. They alternate. That's 2y. So this will be 2y over there. Also alternate angles. Oh, and there's one here that I'm going to need most probably. So those two are equal. That one is equal to this one. Oh, that's beautiful. That is stunning, because now if you look carefully, we've got an isosceles triangle. AC is equal to AN. So let's argue that first of all. A1, we let A1, which is equal to A2, we're going to let equal to X. B1, which is equal to B2, we're going to equal Y. And C1, which is in any case equal to C2 because it is an angle bisector, is Z. Remember, we're not proving that this is an angle bisector, it is one. We need to prove that it shares point P, so that it's concurrent in that point. And we're going to use Ceva to argue that right at the end of our work. Okay, so if I now look at triangle, so if we go in triangle BDC and in triangle NDC, we'll sort the order out just now once we've proved anything, or something rather. Angle A1, which belongs to, this is B, angle BDA, not BDC, BDA. Angle A1 is equal to angle N down here in the other triangle. They are alternate angles that are equal, and the lines that are parallel is AB parallel to NC. Then we also have, what else can we say? We can say, angle C1, 2, 3. Angle C3 here, the little angle here, C3, which belongs in that triangle there, is equal to angle B1 and B2. And for that, the same reason, the alternate angles that are equal. So we don't even have to go and state that these two vertically opposites are equal. We can now immediately claim that ABD, triangle ABD, is similar to triangle ABD, so CND. Okay, ABD is, NC and D. Okay, there we go. And why is that so? They're equiangular. Okay, now we've got that going for us. So what can we make from that? Well, if we want to use Ceva, we need to find a DC and a BD. Okay, if we want to use Ceva, we need to use BD and this DC over here. We need expressions for those. Okay, so let us see what I do have. I have the side here. Let me just indicate these. That there will be the side opposite C, which is small c. This whole side here is the side opposite angle B, which is small b. And as per convention, this will be side A. Okay, so now what can I say? I want something about DC. So if I want something about DC, I'm supposed to use those last two over there. So I need to use BD, in any case on this side. Now what else do I have? I have AB. AB is C. And yeah, let's use AB because we have it, and then we've got to use NC in that proportion. So we say, let's start with AB over BD is equal to NC, first two over last two, CD. And this is sides in proportion. That's why that is true. Okay, so let's have a look. Let's see what we can do here. We have NC. We don't really, look, there's our beautiful, look at that. The fact that these were equal. Also, let's just go also, A2 is equal to N1. They both equal X. So therefore the side AC is equal to the side NC and is equal to the letter B. Okay, so what do I have now? I have that BD over DC is what I want to get to eventually. So let's get AB in. AB is C, so I've got C times, or C for AB over BD is equal to NC, which is AC, and that is B over DC, or CD. So what happens here is what I want, and I want BD over DC, and BD over DC will be C over B. Okay, so we've got this ratio, or that over that is C over B. C over B. Okay, now what does that tell us? What does that tell us? Let's look carefully. It tells us that this over that is equal to C over B. Look carefully. BD over DC, go back to B, is C over B. That is for that line AD. Now similarly, we can show that by doing exactly the same type of constructions, but this time through B, we can show that CF over FA is equal to A over C. And also then that our third line, angle bisector, there deals with AE over EB. AE over EB, go back to A as B over A. Now I'm going to say this again. How can we show this? By constructing first of all a line parallel to AC through B, following the same argument. A line parallel to BC through A, produce this side, follow exactly the same argument. Okay, now we pull in the big guns. By Ceva's theorem, we're going to now test for concurrency. Okay, so let's start with B. BD over DC. And if this product is 1, CF over CA, if this product is 1, then these red lines are concurrent at P. Multiplied by AE over EB. Remember, you start at any point. I could have started that vertex, this one, or that one. So CH over that times that over that times this over this. Okay, BD over DC was C over B. CF over FA, CF over FA, I wrote let me just see, CF over FA, it happens when I talk. Okay, so where's the CF over FA is A over C. Multiplied AE over EB, let me just check, yes, AE over EB is B over A. And as we hoped it would happen, this product results in a number 1. Therefore, what can we conclude? The lines, or the angle bisectors, AD, BF and CE are concurrent at the point, concurrent has 2 R's, at the point P. Okay, so that is a quick way for us to use Ceva to prove that. Let me just kill this thing here, this big banner there. You can see what I've done. We've shown, using Ceva, that the angle bisectors are indeed concurrent. Okay, folks, so please, you can see I didn't use any advanced maths. I just had to decide what am I going to do to create the necessary on this diagram that I can use the maths that I already know, the Euclidean geometry that I'm familiar with. Nothing fancy here. Parallel lines. From the parallel lines we generated similar triangles. From the similar triangles we generated proportions. From those proportions, we needed these proportions because we wanted to use Ceva. From them we then multiplied all the ratios together that we got, and we see that that product gives us 1, which then tells us what Ceva has claimed, that if this product is 1, the Cevians, or in this case the angle bisectors here, will be concurrent at the point P.